Okay, so in this morning's first lecture, we talked about symmetries. We found BMS and extensions thereof. And we saw that for these super translations, there is an actually potentially observable effect associated to it, which is the gravitational displacement memory. So on the one hand, we thought about something maybe a bit more abstract, which are symmetries. And on the other hand, we discussed something that observers, relativists, might be interested in. Now we're going to go to a completely different arena. We're going to go to something that quantum field theorists would think about. So this will be in the context of gravitational scattering, so scattering involving gravitons. And it will involve, again, the infrared sector of the theory. So we'll talk about low energy or soft physics of the S matrix. So how many of you have learned in your quantum field theory course about soft theorems? Okay. I assume soft photon theorem, not soft graviton theorem. Okay, so we're going to jump right at gravity. We'll motivate it. We'll not go through every detailed step of the derivation, but we'll motivate what these soft theorems are. So we start with an n-particle S matrix, which I'll denote by AN. And this is just looking at the transition between some in and out states, given by particles with momenta. Let me label them by pi. So I runs from 1 to n. And if we want to consider particles with spin, for example, we could just look at graviton scattering, then I would also have some helicity Li. So those are my n particles whose energy I will not take very small. So they will be referred to as hard particles. So hard. And these can be either massless particles or massive particles. So it could be massive scalars, for example, or something else. And then we will consider an extra, in addition to these n particles, an extra massless particle with momentum k. Because it's massless, I can describe its momentum 4-vector by 3 labels. There's an energy scale called omega, and then there's a direction. There's a null vector that points you towards where the graviton goes, so this will mark a point on the celestial sphere. So, yeah, let me call it some point on the sphere Z and Z bar. Okay? And this will be a graviton, so the helicity will be plus or minus 2. And then what we're going to do is we're going to take this particle soft, which means we'll take the energy to 0. Okay? So we have these n hard particles, and we have this one extra soft particle. And what we want to do is we want to look at the S matrix that involves this extra massless soft particle. So let's say we have some scattering process here with some incoming particles, some outgoing particles. Those are the hard ones. And then I'm going to attach somewhere. So it could be either on the internal line. So this is the one of these incoming momenta, or I could, so this would be out, I could attach this massless graviton to an outgoing line, or I could also look at some internal line and attach the graviton to there. So this would be an internal line. So those would be external, in and out, or some internal line. anywhere in the blob, in principle. But we're going to see that we don't have to worry about that, at least not to leading order in the low energy expansion. So now there's a statement that if you attach a soft graviton to your n particle scattering amplitudes, it turns out that this n plus 1 particle scattering amplitude factorizes into an n particle amplitude times some factor. So to leading order in this low energy expansion, as I take energy to 0, it turns out that this n plus 1 particle amplitudes become an n-point amplitude. So it relates an S matrix with n plus 1 particles to an S matrix with just n particles. So this is a factorization. Okay? So let me draw this again. And let me, for illustrational purposes, just draw one of these. So I'm attaching this soft particle to this outgoing line. What happens as you take the energy to 0 is you do a low energy expansion, and what you will find is this n particle amplitude multiplied by some factor, which I denote by S0. And this factor here will go as 1 over the energy. So there's a pole. And this pole here, in this soft limit, also has a name. I guess many people worked on the low energy limit back in the 50s and 60s. There's very nice work that Weinberg has done on this, also relating to gauge redundancy and symmetries. So I guess this is often called Weinberg's soft pole. But many other people have worked on this question in gauge theory and in gravity. And the statement is that this factor here that comes with the pole in 1 over omega is universal. What does that mean? So we're doing this low energy expansion, so the pole is just the first term here. There's other terms. Turns out that this first term here factorizes into an n-point amplitude times something. And in principle, the terms that follow after this leading order pole may not be factorizable into an n-point amplitude times something else. Okay? So in general, what is this dot dot dot? There's in general infinitely many terms whose details, first of all, which don't factorize, and whose details depend on the specifics of the theory. While this universal piece does not. So the only thing this universal piece cares about is this 1 over omega pole and a functional form that depends only on the momenta of these other particles that are involved in the process. Okay, it depends on the soft momentum that we have taken to 0. It depends on the polarization of the graviton. But other than that, it only depends on the momenta of the other particles. It doesn't depend on what theory you're working on. It doesn't depend on whether these particles are scalars, whether they're particles with spin. It doesn't depend on the theory, whether you're on Einstein gravity, whether you have minimally coupled gravity or something else. It doesn't depend on any of that. The only thing it depends on, aside from the polarization and the momentum of the soft graviton, is the other hard momenta. So this is a pretty cool statement. No matter what n-point amplitude you have, if you attach a graviton whose energy you take to 0, you will always, at leading order in the soft energy expansion, an n particle amplitude multiplied by this pole and a form that is very simple and depends only on the momenta. So in order to derive this statement, actually the only thing that we need to know is how we attach this extra soft graviton. So essentially what this means is we have to look at the extra vertex that we create by sticking an extra graviton into this diagram and the extra propagator that we create. Because now there's like these two external particles, at least in this diagram, and we have an extra propagator and an extra vertex. So let's do that. So we're gonna look at, in order to show this factorization, we're gonna look at the simplest case. We take the soft graviton and then let all the other hard particles be massless scalars. Okay? At the end of the day, it will not matter. It will not depend on that, but this is just for ease of computation. So we're looking at a soft graviton plus a bunch of hard massless scalars. If you write down the action for a massless scalar minimally coupled to gravity, and you work on in a perturbative expansion, so we take the metric to be given by the flat metric plus an h mu nu, so gravitational perturbation with some coupling where kappa is square root of 32 pi g, Newton's constant. So if we do that, we can extract from our action the interaction term, which takes a very simple form. So then the interaction term in the Lagrangian is given by one factor of the coupling, h mu nu dotted into the stress tensor. So yesterday I made a remark about how we organized our sort of expansion. We discussed yesterday and this morning an expansion of the metric in large R, where we didn't talk about coupling at all. So this Bondi-Sachs formalism does one over R expansion, not talking about kappa. Here I'm doing a different kind of expansion. It's a perturbative expansion, where I perturb flat space by a piece that comes with a factor in the coupling. So this is another way to organize the computation. And at leading order, these just give the same results. Okay, so this is suitable if you want to connect to scattering physics, okay? Because there we do perturbative expansions in the coupling. Okay, so this is now our interaction term. And for a scalar field, the matter stress tensor, so matter mu nu, well, we know what it is. We can easily write it down. It's d mu phi d nu phi minus a half eta mu nu d rho phi for massless matter. Okay. So now we're going to work this out. We're going to work out what the vertex is and what the propagator is. And to do so, we're going to look at what we stick in for the scalars and what we stick in for the graviton. So for scalars, we work in ordinary quantum field theory. What are the asymptotic states that we usually use? Plane waves. So we're just going to write down for the scalars some plane waves. The scalars are determined, are given by they have some momenta p, like that I gave here. So p dot x, so that's the space-time vector, not to be confused with the small x that I'm using for the sphere. And then we have the metric, well, the graviton perturbation. So this is given by some polarization tensor and another plane wave, e to the I k dot x. I'm going to choose this polarization tensor, epsilon mu nu. So this can have either plus or minus helicity. I'm choosing it to write it in a form, well, actually, I don't need this. So this polarization vector is such that if you dot it into the momentum of the graviton, that this is 0. And also, if you compute the trace, so epsilon mu nu, eta mu nu, that this is 0. This is my polarization vector. And now, with this input and the matter stress tensor, I can now read off what extra vertex and what extra propagator I create by sticking an extra soft graviton into the S matrix. So let's start with the vertex. So there will be some I from some conventions. There will be some factor of the coupling at the vertex. And then I will have the polarization tensor. So we have to look at this interaction term, right? So you look at the form of this energy momentum tensor and what I just wrote down for h mu nu. Well, you compute this thing, and what you will find is epsilon mu nu, and then twice the momenta p mu, p nu. So this is homework, working this out. And I've done this. So, okay, plug in phi here. and then work to leading order in the momentum. So this is what you get by plugging in the stress tensor, and then there's some order. I've dropped here order k terms, but since k is given by omega times q, and we take omega to 0, this goes to 0 at leading order. So this is just what you get for the vertex. Okay, simple exercise, plug in these things in here, work out the interaction term, and this is what you get. Now let's look at the propagator. And let's now, we could include massive scalars, so I will also write down a mass term, which for massive scalars we can then drop. But to be more general, let me just add that. So if you stick an extra graviton in here, you will create an extra propagator. So let's look at what the propagator looks like. So again, there's some factor of I. And then because the momentum of the graviton comes out with momentum k, and that incoming particle has momentum p, or you can do the same for the outgoing one, the propagator will be given by, so if I do this for the outgoing particle, I have k, I have p. I guess I'm doing this for the incoming one. So you get p plus k squared, and if the matter was massive, you would also get an m squared here. Okay? Yes? What do you mean? So these are contracted. So I take this, and I plug it in here. Is there confusion? Yeah. It's contracted here. Okay, so let's work this out. So what is this? So let me just write out what this, the sign depends here on whether you look at the sticking it on the outgoing or the ingoing. So either there will be p plus k or p minus k. Work with this, write it out. So this is a k square plus 2p dot k plus p square. And if the matter was massive, there would be plus m square. And now we look at the physics. So if we so the external lines are on shell. What does that mean? Well, if our graviton, this is an outgoing particle, it being on shell, since it's a massless particle, means k squared equals 0. If our matter was massive, then the outgoing legs would have p squared equals m squared, or minus m squared, I guess, in the signature that I'm using. If it was massless, it would again be 0, so I've also covered the massive case here. And then what about the internal lines? Because I also said that we could attach the soft graviton to an internal line. Well, an internal line is never on shell. So there's a difference between these two as far as this propagator is concerned. So k squared goes to 0, p squared goes to minus m squared. So I'm left with this p dot k. So let me write it. 2p dot k. So what does that mean? So I'm taking the energy of that graviton to 0. So k mu is omega times something, some q mu. I'm taking omega to 0. So this will produce a pole in the energy, okay? If you have internal lines, they're never on shell, so I don't get this cancellation. So you will not get this pole, okay? So at leading order in the soft expansion, you don't have to worry about these diagrams. All you have to worry about sticking the soft particle onto an incoming external or an outgoing external particle, okay? Okay, so this is what we have to do. And then, so you can either stick it in here, you can stick it out there, and then you have to sum over all the choices that you can do. So there's a couple of incoming particles, a couple of outgoing particles, and you have to sum over all of them. If you do that, because the internal lines are never on shell, so I don't get these cancellations that I wrote. So I don't get k squared equals 0 or p squared equals minus m squared, and so I don't get what I wrote on the right-hand side. The right-hand side, if you have just soft particles sticking to external particles, gives you a pole in the energy. If you have internal particles, you won't get that pole. So you would get something finite in k. Or like some finite expression that doesn't depend on omega. An order 1 term in the energy, if you wish. And this is subleading to this 1 over energy pole. So if I'm looking only at this leading term here, then all I need to worry about are external lines. Yes? There's no what? Oh, yeah. I'm just telling you that you don't have to worry about loops about internal lines for the leading soft term in the expansion. You will have to worry about it for the next term. You can think of these diagrams as, so this is a blob where you do your renormalization of UV divergences and so on and so forth. Now we're going to stick in a massless particle. There's 3 places where you can stick it in. The third place here doesn't play a role because it's subleading compared to these 2. So for this statement, actually all that you have to worry about is essentially 3-level physics. Loop effects will come into this dot, 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 and they will be very crucial. But for this leading term, they don't matter. For internal lines, the right-hand side will not have a 1 over energy. It will have a energy to the 0 term. And this will match onto the dot, dot, dot here, the next term being of order energy to the 0. And we will talk about that. But let's stick with the leading term for now. So what we have here is that this p plus k squared turned into p dot k, and k goes to 0, because omega goes to 0. And so this gives us a pole. Now, dot, 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 you do this now. So you look at this for sticking it to the incoming, the outgoing, and then you sum over all incoming and outgoing particles where you can stick it to. This is a homework exercise. You sum over all the external particles. And what you find is that this soft fact over there takes a very simple form. So there's a sum over all the n hard particles. Then there is a sign that depends on whether they're incoming or outgoing. So plus minus 1 for in or out. I forgot which way I chose here, but it doesn't matter. Then there's a factor of kappa over 2. That's that kappa over 2. There's these 2 factors of the momenta, the p mu, p nu, but now for each hard particle pi. Then there's this pole, p dot k, so pi dot k. And then there is the polarization tensor, epsilon mu nu. And I can add a label plus or minus here depending on whether the graviton is positive or negative helicity. And you see that that 2 canceled against that 2 over there, so this is all you get. Okay? So this is an extremely simple formula, which, while we did it for scalars, it doesn't care about the other details of the hard particles, and it also doesn't care about the theory. We derived it for some particular one, but it doesn't care. It only cares about the hard momenta, which are these pi's in there. All right? So let me write this down again. So we start with an n plus 1 point amplitude with a plus minus for, depending on whether this extra graviton has positive or negative helicity. And we find that the leading term in this low energy expansion goes like 1 over omega. So that's this piece. So actually, let me write this in a slightly different form. So the k here is omega q mu. So let me just pull out this 1 over omega here, and then let me call this whole thing S0 hat. So this S0 hat now no longer has the omega inside. I pull it out. S0 hat, and the plus minus for the helicity of the graviton. And then there's dot, dot, dots. And the leading term here multiplies an n-point amplitude where the soft particle is gone. Okay? Now, was that clear? Question. Sorry? I think I do use the limit because so for example, one thing that happens is that I have not written it out explicitly, but we have momentum conservation, so there will be delta, Dirac deltas, right? And there's a Dirac delta for an n plus 1 amplitude, and on the other side, there should be a Dirac delta for an n. So you need to take the soft limit also there. Yeah. I'm, skipping some steps here, but I hope this heuristic derivation, I hope that you can follow this. And the beauty is that the result is really simple. Now, there's another nice thing that happens, which is when you go to the next order here. So it actually turns out that the next order also factorizes. There's an omega to the 0 term and an s hat that I might call 1 plus minus. And then there's like order omega terms. And then in principle, there are terms that are not factorizable in this way. So it turns out that there are 3 terms actually that are factorizable. And these two, this is the famous, like, what you might call Weinberg soft theorem, soft graviton theorem. And when was this? 60 something. 65, I think 65. Can you guess when this was found? 2014. It's insane, right?
So why is the technology that has developed?
Yeah, so in order to find this term, and what I'm doing here is working still at tree level. So I'm actually ignoring loops. Like, I'm ignoring loops. I'll make some comments later on. But even just working at tree level, there's some technology that goes into showing this, which relies on this like spinor helicity formalism and some more modern amplitudes techniques. And this was so actually these two, the factorization of these 2 terms was shown by Caggiaso and Strominger in 2014. And this one here also has a very nice form that you can write down easily. So this has an I now. There's a fact of the coupling. There's also a sum over all the hard particles. There's a sign. And then, can you maybe guess how I should change this formula to write down the subleading term? So the next term will be of order 1, so it shouldn't have a pole. So if I write it in this form and I write a kappa downstairs, there should also be a factor of kappa upstairs, right? So I will in fact still get a pi dot k, but there will also be a k upstairs. And in fact, since I introduced already some form that has the omega taken out, so if I have a k and a k here, the omega drops out, so I can just write q. And then, well, there's still the momenta of the hard particles, pi, mu. Okay, let me write this q over there. So there's a q, rho. There's a polarization tensor still, epsilon plus minus mu nu. But then there's an object that has to have 2 indices, not just 1, so that I can contract this. And this object, so here we had the dependence on the momenta of the hard particles. This object depends on the angular momenta of the hard particles. So I for each particle and then 2 indices. Okay? So this involves a much more complicated computation, but it fits also in one line. Okay? there's results for gauge theories. Actually, I mean, before this soft graviton theorem, there were soft photon theorems, which date back earlier. There are also subleading soft photon theorems, which also date earlier. You can ask me in the Q&A session. I can tell you what happens to asymptotic symmetries and soft theorems and so on in gauge theory. We can talk about that. Maybe we'll clarify some things, but just for time reasons, and this is a course on gravity, I have not included it in the lecture per se, but we can talk about gauge theory. Okay, so now let's try to squeeze out some physics of these formulas. So let me first note that this polarization tensor that we have introduced was defined by saying that epsilon mu nu, k mu is 0, and epsilon mu nu, eta mu nu is 0. And so it is defined up to shifts that satisfy this. And the shifts are given by some function, well, some vector that depends on k and k itself. If you shift epsilon mu nu by this expression, so it goes epsilon mu nu plus eta mu of k nu, then, and you stick this into this soft graviton theorem, the leading one that we have just derived, then what you find is the following. The leading soft graviton factor so this was S0, also shifts. And it shifts by the following form. So S0 goes to S0 plus something, and that something is given by the sum over all particles, cap over 2 pi mu pi nu. And then instead of this epsilon, we have this lambda mu of k and this k nu divided by p dot k. So I have put back the k in this expression. And what is this? Well, let me pull out everything that doesn't depend on this sum over I. So I can pull out this lambda, and then I'm left with the sum over I, eta I, p I mu. Because you see that that k dot p canceled against that k dot p. So I'm left with this p mu, lambda mu, which I can pull out of the sum. And then there's this eta I. So what have I done here in doing these shifts? So this shift was nothing but a gauge transformation. My epsilon mu nu, defined by this, was defined up to a shift. That shift here is a gauge transformation for gravitons. And what we have found is that when you do this gauge transformation, the soft graviton factor shifts. Now, if it shifts, if it is not invariant on the gauge transformations, then we have a problem, right? How do we get out of that? Yeah, look at this expression. We're summing over all the momenta. That sign just tells you whether that momentum came in or came out. So we have to keep that sign here. So that is 0, right? So the soft graviton factor does not, in fact, shift. And this is because of energy momentum conservation. Okay, great. So then I told you that there's a subleading soft graviton factor. That beta also does not shift, right? So let's look at what it does. So under the above gauge transformation, S1 shifts by the following. There's some expression which I will simplify, and then what you're left with is k mu, lambda nu, sum over I, eta I ji mu nu. What saves us? Angular momentum conservation. This is again 0 by angular momentum conservation. So these are the global conservation laws that you can extract here by demanding that the soft graviton theorem is invariant under gauge transformations. Or alternatively, you could say, if I impose these symmetries, then I can show that the soft graviton theorem is gauge invariant. So whichever viewpoint you choose. Let me make a comment to something that we said yesterday about the S-matrix bootstrap. So there are some conditions that you use in order to try to constrain the S-matrix. And some of the constraints, I mean, this is also related to CFD bootstrap, where you also start with some simple assumptions, some axioms that you want to satisfy. Gauge symmetry is often something that is used, or some symmetry is used, and you can use one or the other to infer, in this situation, to infer the other one. There's something else that secretly is going on here, which is something that you all know, which is the equivalence principle. So I have not said this, but we have assumed that all the particles couple to gravity in the same way, so that kappa did not depend on what particle I was using. There was no kappa I. If there had been a kappa I, then this would be inside the sum, and then what do I do? So if you assume the equivalence principle and you assume gauge symmetry, you find these conservation laws, or you choose 2 of the 3 and then you find the other one. All right? So now, for the rest of this lecture, I want to tell you how this is related to what we've been doing before. All right? Any questions? Is this all clear? I don't see people nodding very, yes? Okay, good, excellent. So how is now this related to BMS symmetry, and how is this related to memory effects? So let me recall something that we said before, which is that we looked at charges on the future and the past boundary, and under suitable ways of relating the past and the future, in particular the symmetry parameters and the physical quantities like mass aspect and the angular momentum aspect, under some assumptions of how they are related to each other in the past and the future, we find conservation laws between square minus and square plus. So you compute Q minus here and Q plus here. And if you remember, these charges contained symmetry parameters, either this function of the angles or this vector field of the angles. And so these are not just your global charge conservation laws. These conservation laws contain functions that are arbitrary ones on the sphere. So you might say that these are charge conservation laws at every angle. Because of these functions on the sphere. What we now want to do is so these charges come from symmetry transformations, and we now want to derive some Watt identities for these symmetry transformations. And we want to relate these Watt identities because this is all about low energy physics. So here we're going to long distance, while here we're going to low energy. Well, those are kind of the same thing, right? So there should be some relation between energetically soft physics and the long distance physics that we use to discuss symmetries. So we want to derive some Watt identities that relate scattering amplitudes and express the dynamical consequence of the fact that conserved charges commute with the S matrix. So I'm going to say charges, they should commute with the Hamiltonian, right? But, and the S matrix is like e to the IHT, as t goes to infinity, right? So the charges that commute with the Hamiltonian should commute with the S matrix. Once I elevate this classical charge conservation law statement to 1 at the level of the S matrix. All right? So what we want to show is the following. We want to start with an in-state. We want to act on this in-state with our charge. So let me say what I want to, this is what I want to say. I want to have an S matrix statement that says Q commutes with S. So this is what I want to show. Now, if I wedge this between in and out states, I have to pick the Q that's in the past next to the in state and the Q that's defined in the future next to the out state, all right? So that's why there's a Q minus here, then there's an S, and then there's a Q plus next to the out state, okay? And so the statement is, I want this S matrix element to be 0. That's the question. If this is true, if we can show this, then we have shown, and these Q's are either BMS super translations or super rotations. If this statement is true, then we have shown that BMS is a symmetry of the S matrix. And that would be pretty cool. Okay, how do we show this? So now I'm going to go back and make some statements related to the covariant phase space that I got a question on. The question was, well, we are computing this symplectic structure on some Cauchy slice sigma. And then I want to sort of push it to the boundary. Why do I get something, some charge that depends just on the past of the future boundary or the future of the past boundary? So let me say a few more words on how you compute this symplectic structure. So we say that we want to compute this on some Cauchy slice. I'm gonna use shorthand and say that this depends on 2 variations. I'm dropping the fields here. This is an integral over this Cauchy slice over some sigma mu, omega mu. Let's say we have massive matter and radiation, so gravitation and radiation. Then we have to worry about this null infinity piece here. And massive matter goes to this time-like piece here. And the same we have to do with the past boundary. So if we want to push sigma to the boundary, we have 2 components. We have the scry component and we have the time-like component, yes? So let's say there's an I plus and a minus component, and this boundary is in union with the null part, so scry plus or scry minus. It still depends on 2 variations, and we will pick one to be our asymptotic symmetry transformation. So super translations or super rotations. And we said before that if we can, once we plug in the fall-offs of the fields and the symmetry transformations, if this quantity is integrable, we can pull out this other variation and have a well-defined charge on the future or the past boundary with respect to the symmetry. This is the charge. So this is the thing that I'm sticking in here. But what is it made of? So there's a future component, a future timeline component, future null component, and the same in the past. So in the very beginning, in the first lecture, we talked about how we go to this place that is actually singular. So we said, well, we use these hyperbolic slices in the future and in the past light cone. And these hyperbolic slices were labeled by some coordinate tau. So in order to go to I plus or to I minus, I have to write the symplectic structure, this expression, in terms of the coordinates used in the slicing, and then take tau to the future or tau to the past. So to the plus or minus infinity, while keeping the other coordinates fixed. So in particular, there was a coordinate rho, which we have to keep fixed. And that takes us to I plus or I minus. And this piece that we get in terms of charge will have a name. It will be called the hard charge. And why so? Well, because this is about the matter that goes to the timeline boundary. So there's a piece in this symplectic structure computation. This gives a contribution to this charge, which just depends on the hard particles that reach the future or that come from the past. Then there's this Cry component, because we have radiation. In our case, we have gravitational radiation. And this Cry component we know how to get. That's what we did in the very beginning. Null infinity is reached by taking R to infinity and keeping either U fixed on the future boundary or V fixed on the past boundary. And this will give us a piece of the charge which, well, can you guess what it's called? Called Q soft, because this is about the low energy radiation that reaches null infinity. And so you add up these two pieces, and these then give the total charge. And the total charge is what is stuck in here. All right? So much about that interlude. No. So I'm now telling you the piece that I skipped over, because it's more useful to have this fresh in mind now. In order to compute this, you have to take into account all contributions. If you have massive matter, you have to take into account this. And then you have radiation, where you have to take into account the null boundary. We could focus on massless matter. Massless particles don't go to I plus and to I minus. But there's a non-trivial component at the future boundary, how they will contribute. And then I will have to modify this a bit, so we don't need this part here. But there will also be a soft contribution, which just comes from the gravitons. And let's say we have massless scalars, so then they will contribute to like a hard massless scalar charge. So this is a little bit more confusing to think about, which is why I, for the meantime, went to massive particles. But there will be two contributions either way. Either it's massive matter or massless matter, which have an energy that's bigger than the soft energy scale of the graviton. And then we have this extra soft contribution, which comes from the radiation. All right? So now why did I tell you how this works in more detail? I told you about this because this split into a hard and soft part is actually very convenient. So let me do this here. So this being 0, showing that this is 0, is equivalently expressed in the following, where we take the commutator of the soft charges with the S matrix and say that it has to be equal to minus the commutator of the hard particles with the S matrix, hard charge with the S matrix. That's just the same thing. So showing that this is true is just the same thing. Okay, so what we want to show here is that this soft charge has something to do with the soft graviton that we stick into the amplitude. So soft graviton insertion. And here what we want to show is that the hard charge is the other side of the soft term, yes? So the only thing that is different to the scattering process, in which the n particles are involved, is this appearance of the soft charge. This we want to show has to do with sticking in a soft graviton into the amplitude. Then we take the energy to 0, and we get this factorization in the n hard particle amplitude and the soft factor. So what we want to show here is that the right-hand side here is actually the soft factor times the hard amplitude, the one without the soft graviton. So that piece, so there's like S, let's say we're looking at the leading soft graviton, and then dotted into out S matrix in. No soft particle. And here we want to show that this is equal to out and then some creation or annihilation operator. Let's say we stick it in the out state, then we want to annihilate that soft graviton with some helicity. Roughly speaking, this is what we want to show. That this equation follows from the soft graviton theorem. Okay? So I'm actually not going to go into the details of this, but let me just say one more thing so that it becomes clear why the charge that I wrote down for you this morning can be recast into this soft and hard split. So we had this super translation charge. Let's look at the future boundary. We said that it's integrated over the sphere at the past of future null infinity. There's the Bondi mass aspect and this arbitrary function f. So what you can do now, you can massage this expression. We're going to go backwards. So here I told you the way to start is the covariant phase space formalism. You run this game, and out you get something that you could call soft and hard. Now we're going to take the final expression that I gave you in the morning, and we go backwards to land back on this split expression. So what we're going to do here is we're going to integrate by parts to get back the u integral, okay? Integrate by parts so that this integral over the boundary of u is an integral over all of null infinity. So all of square plus. There's a u integral. Now, if I want to write this as a u integral, I have to take the u, the derivative of everything that's inside. But the only thing that depends on u is this m. So I can pull this f out. And then I have the u of m. And I also have to assume that the contribution on square plus plus is actually subleading. So I have to assume something about how the Bondi mass aspect falls off at the future of the boundary. And if so, then I can relate the integral on the sphere here to an integral over all over null infinity. And this is this line. Now, this expression here tells me about the evolution of the Bondi mass aspect. And we said this yesterday, but we did not actually write down an expression. We said that this has actually a right-hand side that is given by Einstein's equations. So this is not something free. It's constrained by Einstein's equation, and it relates the Bondi mass aspect, in particular to the shear or the Bondi news. So once you plug this in, you will find that the charge actually splits into two contributions. There's a contribution that involves the news. And then there's another contribution which, because Einstein's equation relates the space-time to the matter content, so this will contain the stress tensor. And in particular, this equation will involve the UU component of the matter stress tensor. And now you can maybe see where I'm going with this. So this piece that involves the matter is the hard piece of the charge. So that's hard. And that piece here, which is an integral over null infinity of the news, which has to do with gravitational radiation, is the soft piece of the charge. Okay? So you can either do this computation from the start and arrive at the split of Q hard and Q soft, or you take the expression that I gave you yesterday and you work your way backwards, and you will land on this expression for the soft and the hard charge. Okay? So now the remaining thing that you have to do is you have to plug in the expressions of the soft and the hard charge in here, and then check that this equality holds. Now, this is not a trivial thing to do. You have to massage these expressions. You have to look at how particles behave at large distances. And I'm not going to go through this because this will take another lecture in order to actually show this. But you can believe me when I say that you plug in these expressions, you can verify that this statement is true. The way that this soft charge acts, so this has to do with the soft graviton, the way that this acts here will produce precisely the insertion of a soft particle in the S matrix. And the way that this hard charge acts, so this here, tells you about how the BMS symmetry acts on hard particles. And there's some massaging that you have to do with this expression, which is not obvious, but it will tell you that you land on something that once the dust is settled, you can write as the soft factor that I've written before times the n particle hard amplitude. This is not a trivial calculation, but it is true. And so what this then tells us, that since this is true, we can say that BMS supertranslations are a symmetry of the S matrix. Now, I know this is a lot to swallow. I wanted to at least sketch to you how these things work, because you can say the words, oh, it's a symmetry of the S matrix. What does it actually mean? What are the kind of steps that you have to do? Well, these are the kind of steps, and now with this knowledge, you can now go to the original papers and work out this last step that we didn't do. You can go there and be satisfied to see explicitly how BMS shows up as a symmetry of the S matrix. So now to finish this part about setting the infrared stage for discussing a putative holographic dual to quantum gravity in asymptotic flat space, I can now say three things that are all related. On the one hand, we have discussed asymptotic symmetries. And we have shown this morning that a physical incarnation of the symmetries are what is called memory effects. And then I outlined now that asymptotic symmetries are a symmetry of the S matrix, and they precisely correspond to the statement that there is a soft factorization of the amplitude. So soft theorems are a quantum field theorist's way of saying that we have an asymptotic symmetry. Now, there's an interesting relation between soft theorems and memory effects, because obviously they also have to be related. And this is actually a very simple one. It's a Fourier transform. We work here in energy, or momenta, and we work here in position, like retarded time. So if you Fourier transform the energy to position space, you will recast the statement of soft theorems to a statement about memory effects. And it is really interesting that this was done in the mid-70s. This was done in the mid-60s. This connection wasn't known until a decade ago. And the reason is that these were written down in different languages, they're in different communities. These were things, where you look at, I don't know, black holes being like the sort of elementary particles that you would stick in here. And you have like this, the gravitational memory effect happening when you look at not at elementary particles, but as extended objects. But once you look at them through the lens of a quantum field theorist, then this is related by a Fourier transform. All right. So what I want to do, motivate now in the remaining couple of minutes, is to set the stage for discussing a periodic holographic dual. And the way that I want to introduce this is to say that so we have the S matrix, and Guy kind of outlined this yesterday. So there's various ways about talking about asymptotic flat space, and indeed, many things that have been done over the years or decades have kind of a similar flavor. So the proposals that are being put forth towards a holographic dual are tightly connected to the fact that the S matrix is already kind of holographic. We look at a set of in states and a set of out states. So if we look at like on-shell input, the input is the momenta, right? The momenta in the far past, the momenta in the far future. This is kind of holographic. This is what you stick in, and then you have interesting stuff going on in the middle. There is a way to make more manifest the holographic nature of the S matrix, which is by not working in this energy basis. So this energy basis makes what kind of symmetry manifest? Translations, right? There's a Dirac delta with momentum conservation, so this makes translation symmetry manifest. Here we can jump to position space, and then other things become manifest. I want to switch to a basis that makes not translation symmetry manifest. Lorentz, great. Okay, let's try to make Lorentz symmetry manifest. So we got to find a way to make Lorentz symmetry manifest. And the reason for this is, and I'm reaching a bit ahead, the reason for this is that if you want to have a purely holographic dual on the boundary of asymptotic flat space, and specifically on the sphere, I already mentioned that, okay, there's some 2D conformal field theoriness going on there. There may be some Virasoro symmetry. Well, in 2D, what we want to have is conformal symmetry, right? So CFD, conformal symmetry. And the starting point is global conformal symmetry. Now, what is global conformal symmetry from the point of view of 4 dimensions, or like D plus 2 dimensions? Okay, in Lorentzian signature. So we have Lorentz symmetry in the bulk. Let's say 4-dimensional Lorentz symmetry, which, if you recast it in terms of the action on the sphere at the boundary, becomes 2D global conformal symmetry. This is something that you can look up in Di Francesco. And we'll talk about that. So having global conformal symmetry is sort of the first thing to make like the holographic nature of the S matrix a bit more manifest. So what we're gonna do is we're gonna transform statements about scattering to a different basis that doesn't make energy, that doesn't have explicit energy, but some other parameter. And what this will do for us is that it will make much more manifest what kind of symmetries we have in a deep infrared. Okay, let's start to motivate this. Okay, so to motivate this, we want to recast soft theorems in a bit more water density kind of way, so that it looks like something that we're familiar with in CFD. So in order to do that, let's go back to the very beginning. So we write down Minkowski space in Cartesian coordinates, in these flat coordinates, and then we write it down in our retarded coordinates. And we're gonna, okay, first of all, homework exercise, show me the codon transformation that does that. So what you should find is, well, okay, T is U plus R, that's obvious. But then we have, and so this is like Cartesian vector x1 plus ix2 is given by this expression, and then x3 is given by that expression. And I'm just writing this down so that something that I will write down later will kind of make sense. So what I want to do is I want to look at late times and large radii. So at late times, which is where we define our asymptotic in and out states. So we talked about plane waves. We could also take wave packets, right? So let's say we take a wave packet. And let's again go to massless particles. So let's say massless scalars. Which has spatial momentum P vector. So let's say we take our massless scalar. We write down the free mode expansion. In the free mode expansion, we go to late times and large radii. In this mode expansion, we're going to still work with plane waves, so there will be some e to the I p dot x's. That x will contain time and r. And as you take time and r to infinity, there will be some rapid oscillations. So you have an integral of all the modes. There's some rapid oscillation in the exponent. What that means is that you can evaluate the integral of all the modes in some saddle point approximation. So there will be a saddle point. And that saddle point will be at the special value of this momentum p. So this momentum p becomes localized. Again, at late times and large radii, it becomes localized on the sphere. So the conformal sphere or the celestial sphere, on the conformal sphere near where p vector. So this is a computation that you have to do. There's no shortcut to that. Where p vector is given by omega, the energy of those particles, and then this is a space-time vector, x divided by r, so a unit vector. And if I now use the relation between Cartesian and Bondi coordinates, this expression will look like 1 will be omega over 1 plus zz bar, 1 plus zz bar, z plus for the spatial vector, that will be the first component, c plus c bar, minus I, c minus c bar, and 1 plus cz bar, 1 minus cz bar. So this is just explicitly what you get if you work through this. And now the form momentum p mu has as a first component just a 1 and then this vector. Okay. So this was for the scalar particles, and the same you can do with the graviton. Again, you write down the free graviton mode expansion. You do the same thing. It localizes in a similar place. And so now what we find is that, let me write this out again. So massless matter, I'm going to do this now for all the I massless particles that we want to stick into our scattering process. So there will be some omega I, 1 plus z I, z bar I. Okay, massless particles, let's say scalars. And then the graviton, that was k mu, and it has a similar expression. I'm gonna denote this now by omega k, and by some different variable. And essentially the same thing with the zi's replaced by w's. Yeah, okay, let me just do that. And then there's also polarization vectors, plus minus mu nu. And I'm going to write them as epsilon plus mu, epsilon plus nu, and the same for the negative felicity. So I'm splitting this into two polarization vectors, so I can do that. Yesterday, double copy came up. Well, this is the most trivial double copy relation that you can have for a free particle with some polarization vector and a polarization tensor. And again, the same conditions are for this epsilon that we had before. Let me not write them down, and let me just tell you. And this is, I'm writing this down so that you can actually explicitly verify what we're going to do in the following, which is a rather cool result. So you just stick in some polarization vector of this form, let's say for the positive helicity graviton. And now the reason why I wrote this down is that we're going to use this parameterization of momenta in terms of energy and points on the sphere, stick it into our statement about soft physics of the S matrix, and squeeze out something that looks like a water density in a CFT in a codimension 2 theory. All right, so this is the last thing that we're going to do today. And from now on, I don't like W so much. I don't like this letter. I'm going to use from now on all the hard particles will be given by ZI's, and that soft one, I will denote it by Z, okay? This is not to be confused with, so we used, the whole time we used when we wrote down like Cartesian coordinates and went to Bondi coordinates, we used Z as that space-time coordinate. Now, that's why I introduced the W, because now I'm just looking at the reference point on the sphere where a particle goes. But I don't like W, so I'm going to use Z from now on. We're not going to write the space-time coordinates anymore in terms of U, R, Z, Z bar. But we're going to write Z, and that Z will be just the point where the particle goes, okay? So now use these momenta, and now take take the soft theorems, and write them using those P's. So we had expressions for the soft factor in terms of the hard particle momenta, in terms of the soft momentum, in terms of the polarization vector. Now you just take this and plug it in. And then you find the following. So before going to gravity, let me make a quick detour to gauge theory, and we can talk more about it in the Q&A session. So in gravity, we had the leadings of graviton and the subleadings of graviton. We had energy momentum conservation and angular momentum conservation. If we were to run the same game for photons instead of gravitons, we will also find a soft photon theorem. Can you guess what conservation law this should be related to? No. Charge. Good. So there is charge conservation. And because you already told me that, you should be able to guess what the soft factor looks like. So remember, there's a sum over the hard particles. There's some coupling constant, let's say E. So soft photons. So what should I stick in here? Remember, there were two momenta for gravity divided by P dot K, the soft pole. So again, if I use the head ones where I pull out the 1 over energy, then this will just be Pi dot Q, the null vector where the photon points towards the celestial sphere. I had a polarization tensor, and I had two factors of momenta. How do we go to photons from gravitons? Okay, gravitons have a polarization tensor, and photons. Good, so then instead of the tensor, we have here a vector. In gravity, we had Pi mu and Pi nu, because we'd have to dot this. What are we getting here? We have only one index. It's one momentum, very good. And then we need maybe something else, because we said before that there's some conservation law. So what else should we stick in here? Qi. So we have the charges of the hard particles, right? Okay, good. So this is a soft factor for gauge theory. Then let me write down again. So let's say Nm, gravity. This was, what was it? Similar expression, kappa over 2, eta I, pi mu, epsilon mu, pi dot q. And then the subleading one, again in gravity, was minus I kappa over 2, sum over I, eta I. And then we had pi mu, q rho, ji mu rho, and epsilon. Let's do this. Mu. Okay, you had this before. So those are the three soft theorems that we want to look at. And for the first one, let's focus on the photon one. That's why I introduced this, because that's the simplest one. So soft photon theorem. You take this, you plug in these momenta, and what do we get? We find that, let's focus on the plus polarization, so that's plus minus, and so on. What this will become is again the sum over I. Well, the E will tag along for the right, the QI will tag along for the right. And then if you plug in the momenta that we had over there, and remember again that this is omega times Q, what you will find is that this is just given by Z minus Zi. Okay? It's a very simple expression. So you have an n plus 1 point amplitude, then you have an n point amplitude on the other side, and it's multiplied by this thing. Does this remind you of anything? The ones who don't already know what that is. So if on the right-hand side I have something with n plus 1 particles, on the right-hand side I have n particles multiplied by this factor. If you think of CFT, is there something that this reminds you of? We can talk about OPEs in this context. Here we're taking soft limits, there's some relation. But let me take a Z bar derivative of this thing. What does this become? Dirac delta, we had this yesterday. So then you have left-hand side is some n plus 1 point thing, on the right-hand side n point thing, multiplied by Dirac delta. Does the bell ring now? There's a Watt identity, right? So this turns out to, and what Watt identity is it for? For what kind of object in CFT would that be a Watt identity? That looks like this, and one derivative gives you a Dirac delta. And we're looking at spin 1 particles here. It's a current, right? So there's some current. Let me denote the positive helicity current by Jz. That gets stick into some O1 to the On. If I think of these particles as operators that are creating these particles. And then I get this kind of Watt identity. Well, so this is the correlation function for a current, where when I act with a Z bar derivative on it, I get 0 on the right-hand side up to a contact term. So this is a Watt identity for a current, once I act with del Z bar. So here we're sticking with the kinds of spins that we have in 4D asymptotically flat space. There's something about higher spins that comes in gravity, and we could talk about that. But here we're just taking the plain vanilla soft photon theorem, and we find that if we express it in these variables, then it becomes manifest that this is a Watt identity in Watt. So these O's here depend on the points where you insert it on the sphere. So this is a Watt identity in a codimension 2 theory, in this 2-dimensional theory on the celestial sphere. which is the water density for a conserved current. If we do this for gravity now, yeah, let's do it for gravity. So the reason why I introduced the soft photon here in the meantime is because the soft graviton theorem is a little bit more complicated to see what it is. So the leading soft graviton theorem, if I look at this guy, let's say also positive helicity, I get the following expression. Okay, let me pull this kappa over 2 out here. What I get here is omega I, z bar I minus, z bar minus z bar I divided by z minus zi. Okay, so this is what you get for gravity. Now, does this look like anything familiar? Not really, right? Let's try to make it look like something more familiar. So let's say we take a z-bar derivative. And let's then call whatever this becomes. So the analog to what we would get here, let's call this pz. Because it's also factorizing n plus 1 point correlator into an n.1 times this factor. So let me just call this pz as a placeholder. And then what we find is that this is given by something much more familiar looking. Right? So we just take a z bar derivative of this expression. And what is it now? It's kind of similar to what we had before, right? Except that qi became omega I. Nevertheless, this is still some kind of water density. It just has some less familiar looking factor of the energy up there. Let's do one more thing. So for the stress tensor, sorry, I'm giving it away. So for the subleadings of graviton, this guy here, things are a little bit more complicated. And in order to write down something nice, there's not such an easy fix as taking a derivative and then having look like some water density that's more familiar. I have to do some smearing on the celestial sphere to get something neat out of it. So well, let me first give you the expression just so that you have it. And I'm going to look at the negative helicity graviton here. And this acts on the n plus 1 point quantity. Now this looks like some horrible, nasty thing. Doesn't look like anything we know. But you can turn it into something much more familiar looking. So there's some particular smearing. So I'm going to say just smear on the sphere. It's some special integral on the sphere that I have to do, which I will come back to later. And once you do that, then this expression turns into something that looks like this. And nobody complained before that I've wrote down something here that you don't know what it is. Look at the last line. Is that something familiar? What kind of correlator? So on the right-hand side, I will have an O1 to ON correlator. On the right-hand side, there will be O1 to ON, but then there's some extra guy here. For what extra guy does this look like its correlation function? Yes. Very good. Okay, so this looks like the holomorphic stress energy tensor correlation function. Except there's again a pesky thing. So here we have this omega I, and now here we have this omega I d by d omega I, and then that L I just added because if these particles had spin, then there would be some contribution here. If those are scalars, then this is just 0. Now this is rather pesky, and this comes back to what I said up here. If you want to make things about the S matrix look really holographic, we should go to a different basis that gets rid of omega. And this we have to do here in order to recognize this really as a correlation function for a stress tensor. And why is that? Well, a correlation function for a stress tensor has some number sitting here, right? There should be the conformal weights of the hard particles should sit here. But this is not a number, this is an operator. So it's not yet a correlation function for a stress tensor. This is an operator. It acts on the stuff in there. So what we're gonna do tomorrow is we're gonna change our basis for scattering to one where this thing becomes a number. And then we're gonna say, well, we have a correlation function for a stress tensor, we have a stress tensor in some putative theory, and then we're gonna try to take it from there. Okay, so tomorrow we're gonna try to find the basis that turns these correlation functions into correlation functions in something that looks like a conformal field theory on the sphere. Any questions? This was probably the hardest part. Of today. No, now it gets easier. We have now accumulated all the material, all the background knowledge that we need in order to build a solid foundation for a putative holographic dual. Okay, thanks.